Good morning.
Morning, Jim.
Good morning.
Morning, Jim. Okay, girls. Before we start, any questions? Any questions regarding the bigness parameters? Wavelength period and frequency? No. Oh, shit. That was close. Okay, girls, so we're going to just talk about the seventh and the last acoustic parameter, which is going to just what they call propagation speed. Right, okay. And the word propagation is mainly as just as I said earlier. It's mainly as it's just a fancy word that means to we can say progress ahead or move ahead. So actually as we can just say it's just going to be or we can also say it's we're going to be the speed of sound. Clear? Okay. And what is speed? You can mean it's define speed as as that's going to be as the distance. And whenever we say distance, it's the word length will mean the same. Okay, distance covered in a period of time. Yeah. And if we just look at this definition here, that actually is also gives us the unit for speed, which can be as any unit of distance or any unit of time. Yeah. So you can say something like, yes, centimeter per second. Okay. You can say it's okay, meter per minute or second if you want. It doesn't really matter as long as, okay, yes, it is a unit of distance by unit of time. That is going to be, it's okay, what we can call the speed. Clear? Okay. Did you ladies get that? Okay. Now, as I said, or have mentioned was, okay. So that's going to be the unit. Any unit of distance by unit of time. Clear? Which mainly is okay. Now, whatever speed, and that's mainly as okay, just going to be as okay. That could be a number. We can say as okay, 10 centimeters per second. If that's the speed that we travel at, or if something is moving at a speed of, let's say, as okay, 10 centimeters per second. That mainly mean that okay, yes, in 1 second. Okay, that okay, yes. In a time span of 1 second, it will be able to just okay move across a distance of 10 centimeter. So that's okay. In 10 seconds from now, this object here is okay, starts moving. Okay, at a speed of 10 centimeters per second. In 1 second, it's going to be as okay, 10 centimeters away from this point here. It may as okay be at point B, which is 10 centimeters away from where it started a second ago. Clear? Okay, which mainly mean that okay, is in 2 seconds, it will have moved okay as a distance of 20 centimeters. In 3 seconds, it will have moved a distance of 30 centimeters, and so on. Is that clear? Okay, so as far as okay, as you have any unit of time, or sorry, any unit of distance per unit of time, that's going to be as okay, the unit of speed. Okay, but that's going to be as okay, speed of sound, speed of your car, speed that you walk, exactly. Or in all contexts, yes, okay, speed of sound. Okay, which mainly mean that okay, yes, in XYZ amount of time, the sound wave may have traveled a certain distance. Okay, but that is okay. You can say it's okay, 3 centimeters. Okay. But that speed is mainly as okay going to be the okay, the time that it will take. So you can say it's okay to reach from point A to, let's say it's okay, point B. That point B is okay at 3 centimeters away from it's okay, the starting point. It's all going to be dependent upon the speed itself. How much time does it take the sound wave to cover a distance of, let's say it's okay, 1 centimeter. Yeah, okay, so that will say it's okay, it will take it this much time to reach from here to here, because that was the distance covered in okay as a specific period of time. These are going to all dependent upon the speed at which it is traveling. Okay. Now, ladies, any questions? It goes now. I will mainly as okay, just skip the what you want to call it, the typical value for a little bit. I mean, that's okay. Just says okay. What is going to okay determine the speed of sound, or we can say, okay, what's going to determine, or we can say ultrasound's speed is going to be determined by the medium. Okay. It's mainly as okay going to be the medium, which in our case, yes, okay, is going to be as okay the tissues. That will determine whether it's okay the sound travels, let's say, at a high speed, or whether it's okay the sound travels at a low speed. That speed of the sound is going to be determined by the medium, which will be our tissues. Clear? Just as I said in chapter 2, if you guys remember, that okay, as speed, or we can say okay, a high speed in solids. Then we say, okay, we may have, okay, as the lowest speed was going to be as okay in gases. And then we can say, okay, here we can mean it's okay, squishing something, which is going to be as okay, and intermediate speed in liquids. Which mainly mean that okay, as in liquids is going to be as okay, slower than solids, but still faster than gases. Okay, so speed is only going to be determined by the medium, which is going to be as okay, your tissues. And what I already also have said is that okay, yes, that this change, or because it's okay, varying speed in the medium, or in it's okay, we can say it's okay in different media or different tissues, is going to as okay lead to varying wavelengths in the different tissues or medias. Clear? But it is not going to be the other way around. It was not going to be that, okay, as varying wavelength is going to, yes, okay, affect the speed. So pretty much, okay, due to this, that the changing speed changes the wavelength, that was why, yes, okay, your wavelength was determined not only by source. Okay, where, okay, yes, in that case, okay, in case of the source, okay, it was going to just, okay, be related to, we can say, it's okay, the frequency and period, and we have already talked about that relationship. Okay, but yes, okay, the relationship to speed is going to be that, okay, as changing speed leads to changing wavelength, but changing wavelength does not need to changing speed. Did that make sense? Which mainly as okay, then we just mean the same, that a changed frequency will not mean that, okay, as the sound travels at a different speed. Likewise, okay, at different frequencies or periods or cycles will not cause the sound to travel at a different speed through a medium. Did that make sense? Now, guys, if you look at, so just remember, speed of sound is going to yes, okay, be only determined by the medium. So now we yes, okay, have we can say it's okay, a list of the factors that determines yes, okay, your parameters. You said power, no, sorry, not power, frequency, determined by the source. What the hell you call that fellow? Period, determined by the source. Power, amplitude, and intensity. Now, when we say power, amplitude, and intensity, and we say initial power, initial intensity, and initial amplitude, that is going to be determined by the source. Clear? Your final power, final amplitude, and final intensity is going to be determined by your initial power, intensity, and amplitude, and the tissues. Because what we said was that, okay, as the sound travels through the medium, its power, its amplitude, and intensity will decrease. That decrease is going to happen as a result of what we call acoustic propagation properties, effect that the medium has upon the sound. And that effect is that, okay, as these three parameters here are going to decrease. Okay, but your initial power, your initial intensity, and your initial amplitude is going to be determined wholly and solely by the system, which we could adjust as well. Did you guys get that? Okay. So, girls, if you look in your book, under yes, okay, when they say yes, okay, determined by. The first paragraph mainly says, okay, as that your speed is determined by the medium. Okay, speed is going to be as okay, determined by the medium. Then it goes on to the second paragraph, and I want you guys to yes, okay, mark that second paragraph. Okay, now all the yes, okay, it says all sound regarding frequency. But goes as okay, it's not only frequency, it's also going to be as okay, regardless, period. You can put it that way. And it's okay for that sake, it's okay, regardless, wavelength. Okay, it's going to travel at the same speed through a specific medium. Yeah. So what does that mean? Okay, we already said, okay, as the speed of sound, that's going to, okay, be determined, or that's going to, okay, mainly vary as that sound wave, okay, will travel through different tissues. Yeah. But what it mainly means here, let's say that, okay, yes, we have a tissue here. This is a tissue. Let's just say that, okay, yes, this is a muscle. Clear? Now we may, yes, okay, scan this muscle here, yes, okay, using two different transducers. We may have, let's say, it's okay, high frequency transducer. Let's say it's okay, 10 megahertz. Yeah, we may have, okay, let's say it's okay, relatively less, okay, low frequency transducer. Let's just say it's okay, a 2 megahertz transducer. Did that make sense? Now, when both of these transducers here, it's okay, are going to, yes, okay, you can say it's okay, send out their sound waves. In both instances, okay, the speed at which the sound will be traveling through the muscle is going to be seen. Clear? Okay. Now, practically, yes, okay, the speed of sound through muscle is, yes, okay, 1,500 meters per second. So that is irrespective of, okay, yes, whether we use a 10 megahertz transducer or whether we use a 2 megahertz transducer. The speed of sound in both cases here is going to be, yes, okay, 1,500 meters per second. Did that make sense? Right, okay. But what it actually then means, yes, okay, that sound wave, yes, okay, because yes, okay, speed of sound was, yes, okay, determined by tissue. Because that we, okay, I had a 10 megahertz transducer. Okay. And let's say it's okay that it's still going to, yes, okay, you can say it's okay. Send sound wave, yes, okay, through this medium here, is okay, we will say it's okay, this is a muscle. Yeah. We can say it's okay, maybe it's okay, right next to that muscle, yes, okay, we have, okay, as another tissue. Okay. That's just a fat. Now, this is a 10 megahertz sound wave, okay, or transducer. So it's going to just, okay, produce, okay, as a sound wave with a 10 megahertz frequency. Clear? Okay. But now, yes, okay, as that sound wave is going to just, okay, travel through the muscle. It's going to be traveling through the muscle at a speed of the same 1,500 meters per second. There, okay, as when it travels through fat. Now, fat is a different medium. Okay. And that's going to just, okay, mean it's okay, just make it travel at a lower speed. Okay. Mean it's okay, just 1,450 meters per second. Although, yes, okay, it was the same transducer, which we can say is okay at 10 megahertz frequency. Right, okay, we're at 10 megahertz frequency. So we can mainly say, okay, the period, for instance, for this transducer here was going to be 0.1 microseconds. Okay. Yeah. We could also say, okay, what was the wavelength of the sound wave, yes, okay, produced by the transducer here. That was going to be, yes, okay, that 1.54 divided by 10. Clear? Okay. So we can actually say, okay, that, okay, our frequency was going to be, as okay, this here many millimeters. As it was produced by the transducer. But then that wavelength, yes, okay, would change as it travels through the different medium, because the speed of sound would then affect the wavelength. Clear? Okay. So two different transducers, which you can say that's okay, with two different frequencies. If they scan the same tissue, yes, okay, the sound is going to, or the sound wave is going to travel through through that tissue at the same speed. Where that was okay as a sound wave produced by a 10 megahertz transducer versus a 2 megahertz transducer. The speed of the sound in that specific tissue is going to be different. It's going to be the same. Okay. Whereas if we just had one transducer with a fixed frequency, but as that sound travels through the different tissues or different media, they're going to be traveling at different speeds. Did you ladies get that? Did you ladies get that?
So,
Yeah.
so when two transducers are scanning the same area, it's going to give out the same speed until it gets to a different medium. Then it slows down for each one.
Yeah, because it's going to be the tissue that will determine the speed.
Okay.
Listen, dear. Look here. That's what I said. Okay, I said, okay, listen. Two different transducers, right? Two different transducers, right? One had a frequency of 10 megahertz. One had a frequency of 2 megahertz. Clear? Okay. Now, when you scan the same tissue, here we says, okay, our tissue was muscle. Okay. It doesn't really matter whether we use a 10 megahertz transducer or whether we use a 2 megahertz transducer. The speed of the sound produced by either of these transducers here is going to be the same as that travel through muscle. Did that make sense?
Yes.
Whereas I said, well, okay, now we only have one transducer. We just chose one. It doesn't really matter. You can trick the two. You can say, okay, I don't want 7, I don't want 10, I don't want 2 megahertz. I want 7.5 megahertz. Go ahead, be my guest. That really doesn't matter because the speed of sound is going to be determined by the medium. So whether you have a 10 megahertz transducer, whether you have a 7.5 megahertz transducer, whether you have a 5 megahertz transducer, 2 megahertz transducer, when that sound, or whatever frequency, travels through a specific medium, the speeds are going to be the same. So here's, we just took one transducer, say 10 megahertz. As that sound travels through muscle, it's going to travel at a speed of 1,500 meters per second. Clear? Now that sound, we can say, leaves the muscle and as now travels through fat. In fat, it's going to travel at a different speed, which is going to be 1,450 meters per second. After that, you can say it may come across another medium. Let's just say it's lung tissue. Okay, and in that case, it's going to be traveling at a even lower speed, which is going to be just 500 meters per second. But here is it was the same transducer with the same frequency. Okay, the frequency is going to remain the same. The period of your sound wave is going to remain the same. Clear? But the speed of sound is going to vary as it travels from muscles to fat, from fat to bone or to lung. Okay, and what is going to determine that change in the speeds? That's because the speed of sound is going to be determined by the medium itself. which in this case is okay, was muscle, fat, and lung. Although, yes, okay, we had the same transducer. Did that make sense?
Yes.
Okay. So that's why we said, okay, yes, what is going to determine, yes, okay, how fast or slow a speed travel or sound travels? That's me, yes, okay, going to be determined, yes, okay, what medium is it that the sound is traveling through? So that speed will remain the same irrespective of, okay, irrespective of if it was a 2 megahertz transducer, 10 megahertz transducer, 7 megahertz transducer, it doesn't really matter. Did that make sense? Okay. So that's pretty much okay. That's what the second paragraph of is okay. You can say it's okay. It says in okay, yes, determined by all sound waves, regardless the frequency. Okay, no, it could be a regardless period too. Right, okay. Okay. Travels at the same speed through a specific medium. Which we said here, yes, okay, our specific medium, yes, okay, that was muscle. So regardless the frequency, yes, okay, to travel through the specific medium at the same speed. Now I just give you an explanation and say, yes, okay, this means that a sound with a frequency of 5 megahertz frequency and with a frequency of 3 megahertz travel at the same speed through the same medium. So here they may as okay, so when I say okay, 5 megahertz and 3 megahertz, it doesn't really matter. Okay. Okay. That they will travel, yes, okay, at the same speed through, yes, okay, the same medium. The speed will change if the medium changes. But that will still be the same. The speed will still change, that's okay if the medium change. But that's not the frequency of that of these transducers yet, I would call that. That's me, it's okay, it's because it's going to be, it's okay, a different tissue. So the speed will remain the same in lung, whether it was a sound produced by a 10 megahertz versus a 2 megahertz transducer. Okay. So you can literally say as okay, it doesn't really matter whether you use a high frequency transducer, low frequency transducer. The sound will travel at the same speed through the same medium. So if it travels through solid, it will travel fast. If it travels through a liquid, it will travel slower. If it travels through air, it will travel at the slowest speed of sound. Did you ladies get that? Okay.
I have another question. Well,
Okay, go ahead, yeah.
so I get that when they go to a different medium, the speed will change. But would the both transducers would not be the same in speed, right? Those two would change the speed, right? The two transducers is not going to have the same speed anymore, right?
My dear, your speed is not determined by the transducer.
No, I mean not the transducer. I mean like when it goes to a different medium, the speed would change.
Exactly.
So both of the speeds started off at the same, but they changed the speed when they got to a different medium.
Listen, my dear, your speed of the sound at which it is going to be traveling will not be determined by the transducer. Or you can maybe say, okay, factors that are determined by the transducer will not affect your speed. Let us put it that way. Okay? Or parameters that are determined by your transducer will not affect your speed. What were your factors that affected you or were determined by your transducer? Things such as frequency and period and your wavelength. Did that make sense? Because it says that sound is, or we can say, okay, the speed of sound will be determined by the medium through which the sound travels. Now, for us in this instance here, it's okay, where is going to be the medium? That will be your tissues. Clear? So it doesn't really matter, yes, okay, what the frequency of your transducer is. There's a high frequency transducer, a low frequency transducer, an intermediate frequency transducer. Clear? Okay. Which are going to just, okay, produce sound waves at different frequencies. But when that sound wave travels through the same tissue, whether it was produced by a high, low, or intermediate frequency transducer, they will all travel at the same speed. Did that make sense?
Yes.
Because the speed is determined by the medium. So what I mainly is okay, just want, so I was okay, is trying to is okay. Apply here is okay as what I is okay gave you with okay as an example. Let me say as okay. Two different transducers with different frequencies. But when that sound wave produced by these two different transducers with different frequencies, as okay, travel through muscle. In both cases, okay, it will be the same speed. Whether that was the sound wave produced by by a low frequency transducer or a high frequency transducer. Clear? So as that sound travels through this muscle, it's going to be okay traveling at this speed here. Because that speed is not determined by us, okay, your frequency of the transducer, the wavelength of your transducer, and so on. So it's wholly and solely going to be as okay, the medium that say, well, okay, I'm going to as okay, let the sound travel through me at this speed here. I'm a muscle, so I let you travel a little fast. Well, okay, when that sound wave is okay, comes through as okay, passes through, let's say as okay, fat is going to be a different speed because now it's a different medium. Did that make sense? So if you had just one transducer that produces okay a sound wave, you can say it's okay with a fixed frequency, let's say 5 megahertz. That's its frequency. That's something that was determined by the transducer and the transducer only, right? Okay. But that's its frequency. Okay, we have 5 megahertz. We can say, okay, its period for each cycle is going to be so and so. But as that sound travels through different medium, you can say it's okay from muscle to fat, from fat to bone, from bone to so on, so on, so on, so on. So in different medium, it's going to say, okay, that sound wave is going to travel at different speeds. And what is going to determine whether that speed is going to be high, low, or something in between? That is going to be the medium that determines that. It's not the frequency of the transducer. It's not the period of at which, okay, the sound wave were produced that will determine that. That's going to be the medium itself that will say, well, okay, I'm a muscle, you can travel through me at this speed. It's the same sound wave as, okay, come across, let's say, a lung, the speed will change. Did you get that? Okay. So you can mainly as okay be given as okay an example where they say, well, okay, listen, girls, we have 2 different transducers that scan a specific tissue. You can say, okay, 2 different transducers, let's say, as okay, 2 different frequencies. They scan the same tissue, and they may ask you, which of these 2 transducers here is going to, okay, produce a sound wave that will travel fastest or slowest through, yes, okay, this specific tissue here. Now, most people, yes, okay, may tend to say, well, okay, higher frequency will also, yes, okay, mean higher speed, which is wrong. Because they didn't know, or they didn't, yes, okay, realize that, okay, as the propagation speed of sound was determined by the medium through which the sound travels. And that's why I say, yes, okay, please mark that second paragraph. So that's okay, regardless what your transducer frequency is, as that sound travels through, that's okay, a specific medium, is going to, yes, okay, travel at the same speed. Because the speeds here are not determined by factors determined by the transducer, such as frequency, such as power, such as amplitude, such as wavelength, such as intensity. But it's going to just, okay, be determined by the medium itself. Just like we could say as, okay, if we just had, okay, as a 10 megahertz transducer, okay, that doesn't mean that, okay, yes, that sound here is going to just, okay, travel super, super fast through all these media here. No, it would change from medium to medium to medium to medium to medium. Although it's okay, it was just one transducer with, okay, as we can say, it's okay, a fixed frequency. Why will the speed change? Because the speed was determined by, okay, the medium through which the sound travels. Did I answer your question? Or is there anybody who is in the least amount of doubt? So don't fall. Don't fall for the trick. that, okay, yes, if you're asked high frequency transducer versus low frequency transducer, high frequency transducer may have a high speed, low frequency transducer may have a low speed of sound traveling through a medium. Is that clear?
Yes.
Yes. Good. Any questions? No, girls. We can mean says, okay, say, is the speed of sound adjustable? No. It is not adjustable. The reason that it's not adjustable is that, okay, you won't really be able to just, okay, say, have control upon what media is, okay, the sound is going to be traveling through. Or we can mainly say, okay, speed is not adjustable because, okay, it is not something that is determined by the system at all. Okay, okay. We could adjust the frequency by, you can say, okay, using a different transducer. Okay, we could adjust our power, we can adjust our intensity, we can adjust the amplitude by, as okay, increasing or decreasing, yes, okay, the power output on our system. Yeah, okay. But mainly because, yes, okay, this factor here, which is going to be, yes, okay, your propagation speed is wholly and solely determined by the medium. You can't say, well, okay, I'm sending the sound wave, yes, okay, through a muscle. The normal speed at which sound was traveling through muscle was, okay, as 1,500 meters per second. But I wanted to travel at a slower speed. There's nothing that you can do to just, okay, increase or decrease that speed of sound, because that's going to be the muscle that will say, well, okay, this is the speed at which I allow sound travel through me. So for fat, so for lungs, so for blood, so for whatever. Okay, so it's really not something that we are able to just, okay, control. So that's okay. If we can't control it, it's not adjustable on our behalf. Did you ladies get that? Did you ladies get that?
Yes.
Okay, girls. Now the typical values. Now we can mainly say, as okay, the typical value here is okay, is going to, as okay, of, we can say, as okay, propagation speed. Now this one here is going to be as okay, as super MTK, which means must to know. Okay, girls, and the range of, yes, okay, speed of sound through media range from, yes, okay, as low as 500 meters per second, which is mainly, yes, okay, going to be from air or gas, all the way up to, yes, okay, Oh, sorry. Where were we? 4,000 meters per second, which is mainly that's okay going to be for bone. Clear? Okay. But in the middle of all these speeds here, it's okay, is going to be it's okay, this speed here, which is going to be it's okay, 1,540 meters per second. Or it can also is okay be as okay 1 comma or 1.54 millimeters per microsecond. And this speed here is mainly as okay going to be as okay the speed of sound for as okay what we called soft tissue. Right, okay. Now it's okay. I've been mentioning this as soft tissue is okay for a day and a half or so. And I said, well, okay, this is not really a tissue that we as okay discussed when we did yes, okay, our classification of tissues. Where we said okay, epithelium, connective tissue, muscular tissue, and okay, yes, nervous tissue. So this tissue here is mainly as okay, just a kind of tissue classification, or yes, okay, that has been designed to explain ultrasound and the concepts of ultrasound. Okay, so unless and until yes, okay, specified otherwise, your book will be as okay. This book here is most likely as okay, will be talking about soft tissue. Is that clear? Now, girls, you may on your page, okay, what page is that? 37 in your book. On page 37 in your book, you may see a list or a table of different tissues, right? Table 3.3. Right, okay. Where you mainly can say, okay, the first is lung, then next is fat, then you have okay, a soft tissue, and that's written in bold. And in bracket, it even say average. Then it's going to be liver, then blood, then muscle, then tendon, and then bone. Okay. Now, let me make things easy for you. Okay. The only actual speed that you need to remember the value of is going to be as okay, the speed of sound in soft tissue. So the only value that you will need to remember is that, okay, as what, how fast or slow is it that sound travels through soft tissue? Clear? Which is going to be as, okay, either 1,540 meters per second or 1.54 meter or 1.54 millimeters per microsecond. Clear? So the only actual value of speed of sound through a specific medium that you need to remember is that of soft tissue. Okay? You're not going to be asked what is the speed of sound through lung? What is the speed of sound through liver, blood, blah, blue? Did that make sense? Okay. But, you will have to remember the sequence here. that lung is slowest, followed by fat, followed by soft tissue, followed by liver, followed by blood, followed by muscle, followed by tendon, followed by bone. Or we can mainly say that's okay, if you go from top to bottom, this is mainly as okay, you can say it's okay, the propagation of speed of sound in an increasing order. Is that clear? Now, whether you want to, okay, remember the names of the tissues in this order, or whether you want to make up a mnemonic, that is wholly and solely up to you. You can make whatever crazy mnemonic you want to. Okay? But remember, ear or lung, slowest, fat, soft tissue, liver, blood, muscle, tendon, bone. Clear? You can say, well, okay, the cheat is, well, okay, ear slowest, liquid in between, and then bone, solid, is fastest. Okay. But as okay, I'm not going to be you're not going to be asked, okay, what is the speed of sound that's okay through bone? What is the speed of sound through fat? What's the speed of sound through liver? What's the speed of sound through that's okay muscle? Okay, the only value that you will need to know, and it is expected that you know it, will be as okay, the speed of sound through soft tissue. Did I make myself clear on that one? So the only value that you need to know is that of sound, of speed, and soft tissue, but you need to know the sequence of the tissues from highest to lowest or from lowest to highest speed, whichever way you want to remember. It's up to you. Clear? If you go from the top of your list to the bottom of the list, that's okay. You start from lung to bone. That's mainly that's okay. Your speed in an increasing order because the speed gets higher and higher and higher. Whereas if you go from bone to tendon, that's okay. From bone to lung, that is mainly that's okay. Just your propagation speed in a decreasing order. Did you ladies get that? Did you ladies get that?
Yes. Yes, sir.
So, speed of sound in soft tissue is 1,540 meters per second, which mainly means okay that in soft tissue, the sound actually that's okay, or actually that's okay, or ultrasound actually will be able to travel at a speed of 1 mile per second. It takes 1 second for that's okay, the sound to travel a distance of 1 mile in soft tissue. Clear? Okay. And please, girls,
Can you repeat that, please?
sound travels at a speed of 1 mile per second through soft tissue. That's 1,540 meters is, because that actually becomes 1.5 kilometer per second. So 1.5 kilometer actually is okay, is approximately is okay 1 mile. And girls, please be watchful. Okay. Because it's okay, it is 1,5400 meters per second. And the reason that they put a comma here because it's okay, this is 1,000. Then you go 540. And then the unit is going to change, okay, be meters per second. Whereas if they go like this, 1 point, and like this. Now this is a whole number. And then this says, okay, becomes a fraction. But then you also have to just, okay, make sure that, okay, as you know that, okay, the unit change from meter to millimeter. And in this case, yes, okay, the unit of time is also going to, okay, change from second to microsecond. So it's going to be 1,540 meters per second, or 1,54. Oh, sorry, 1.54, sorry, millimeters per microsecond. Both of these here, okay, are worth the same. And as okay as the speed of sound through soft tissues. Any questions? Now, ladies, if we just look at this fellow here. This speed here, does this number here tell you something? .54. Does that ring a bell? Does the number 1.54 ring a bell?
Yes.
Yeah,
Which kind of bell?
Wavelength.
wavelength.
Right.
Wavelength. And we said, okay, that wavelength I was going to as okay, be there, as okay, measured in millimeters. Okay, there, okay, as the frequency that we use was going to be as okay in megahertz. Clear? Okay. Because, okay, when we have, okay, as a frequency in megahertz, that means it's okay, going to, is okay, mean million cycles per second. Where, okay, as a microsecond was mean as okay, just 1 over million of a second. Okay, so when we talked about the speed of sound in soft tissue, that's where that comes from. Okay. So something that yes, you might have been scratching your heads on back then. Right, okay. But the value, whether you say is like 1,540 meters per second versus 1, or 1.54 millimeters per microsecond, they are the same. Is that clear? Any questions, girls? Any questions? So what I have been trying to just clarify now, since this morning is, no matter what the transducer or systems or factors determined by the system is not going to affect the propagation speed, because propagation speed is wholly and solely determined by the tissue. Okay. And that's why we have that list. And say, it doesn't really matter, whether it's whatever the frequency of that transducer is, whatever the power is, whatever the intensity is, whatever the wavelength of the sound wave produced by the transducer. As that sound wave travels through lung, it's going to travel at speed of 500 meters per second, soft tissue, 1,540 meters per second, bone 3,500 meters per second, something like that. It doesn't really matter which frequency, wavelength, intensity, power, amplitude, so on, so the sound wave has. Is that clear? So that was the list. Now we can mainly assess, the question then arises, what determines, or we can say, what would be as characteristics of the medium that will determine the speed at which the sound will travel through that specific medium? Now we roughly said in the beginning was gas slowest, liquids faster, solids fastest, or vice versa. Yeah. Okay, but there are mainly two characteristics of a medium that will determine the speed of sound. And those two characteristics of the medium, we can say, that determines propagation speed. We already said that, as the medium itself will determine the propagation speed, but they're going to be as characteristics of the medium. That means we'll say, set the speed. And those two characteristics are going to be as first of all, we will say stiffness. The second one is going to be as what we call density. And stiffness and density of what we can mean is okay, we can say it's okay. The stiffness of the medium. And we can say it's okay, the density of the medium. And what we mean is okay, in our instance is okay, we're mean by the medium. Sorry. That's going to be our tissues. Okay. So two characteristics of the medium that mainly is okay will determine how fast or how slow, yes, okay, a sound wave is going to, yes, okay, travel through a medium. It's mainly going to be, yes, okay, how stiff is it that that medium is? And what is okay as the density of the medium. Now goes the question then arises, okay, as what in the blue is stiffness? Now we can mainly say, okay, that means okay, we can say, okay, be an ability to resist compression. So it's okay. You may take, let's say, it's okay, two different things. Let's say that, okay, as we have a sponge ball. And we have, okay, as let's say, it's okay, a baseball. Now, as far as stiffness is concerned, we can mainly say as okay, the baseball is going to have okay as a greater stiffness. There, okay, as the sponge ball is going to as okay, which means okay, just made up of foam. It's going to as okay have the lowest stiffness. Because okay, when we press on a baseball, it's going to just okay be difficult for us to just okay compress it. Why? Because it is stiff. Okay. Where okay, as a sponge ball, a ball which is made of a sponge of foam, it's going to as okay be easy to compress because it has a lower stiffness. Clear? Okay. So a bone, as you can say, okay, a tissue with maximum stiffness is, for instance, okay, going to be bone. Something with okay has a lesser stiffness, especially as okay, if it has a form, for instance, okay, will be something like okay as lung, or even as okay, something as okay, liver. Clear? Now, if you go down like as okay, this definition here is okay, the ability to resist compression. We can also as okay, just say it in another way as okay, the stiffness is going to be as okay, be the inability to compress or to be compressed. So anything that is going to be, it's okay, say it's squeezable. It's easy class has mainly because it is less stiff. Okay. Do you guys remember the last time you went to get blood work done? They may give you that little heart-shaped sponge to squeeze on, right? What is that made up of? It's a sponge. Okay. And me is okay because it's a sponge, that's okay. It's easy for you to just okay compress that because it is not stiff. Had they given you it's okay a piece of rock and say, well, okay, let's compress on that, that's okay. You might that's okay either break your fingers. You're trying to do so. Right? Because that rock or stone is going to be as okay stiff. Or it's going to be as okay, you can say at least going to be as okay more difficult for you girls to, or not you girls, for anybody as okay to squeeze or compress that stone. Okay. Now, so that was characteristic number one. Okay, and how yes, okay, that is going to just okay affect the propagation speed. We'll come back to that in just a little bit. Because the next characteristic is me is okay, going to is okay, what we say density of medium. And here, yes, okay, go, we just okay, relate the density to the medium, but density is still the same. It's going to, yes, okay, be mass per volume. Did that make sense? So here again, yes, okay, girls. We may have, let's say, yes, okay, two balls of the same volume. Their volume is the same, or we can make it as okay, physically as okay, their size is the same. We can say it's okay, same size or same volume. Right, okay. The example that I may use is going to be as okay. We can say as okay. A table tennis ball versus yes, okay, golf ball. Yeah. They both have yes, okay, the same size, or yes, okay, if you hold them side by side, they are going to yes, okay, occupy yes, okay, the same volume. But yes, okay, as far as okay, the golf ball is going to be concerned, yes, okay, that's going to have okay as a greater density. Versus the table tennis ball is going to have okay as a lower density. Because okay, if you cut into a table tennis ball, what is it that you're going to find? Well, it's filled up by nothing. It's me, it's okay, just air. Whereas okay, if you go into it's okay, a golf ball is okay, it is filled up with some densely packed hard material. But here it's me, it's okay, because it is densely packed on the inside with some material that has a greater mass. But the same volume is okay, just cause it to have okay as a greater density. Did that make sense? Okay. So here is okay, whether it's density of okay as a medium or whatsoever is the very same as okay as density in general. So the two characteristics of medium that is going to determine whether sound wave travels at a fast speed or low speed is going to be as okay, how stiff is it that the medium is, and what is the density of the medium. Is there anybody who is in any doubt? Okay. Now the question then just arises, okay, yes, how were these two characteristics here of a medium going to, yes, okay, determine the propagation speed? So we can say, okay, speed of sound in medium and stiffness. Yes, and others I can also say is okay, the same. Speed of sound in medium and density. Now there is a cheat, and the cheat is SS. Because the speed of sound is going to be as okay directly proportional to the stiffness of the medium. And what does that mean? That you can mainly say as okay, the greater the stiffness, the greater the speed. Lesser stiffness, lesser speed. So the less stiff a medium is going to be, the slower is it that the sound is going to be traveling. And then vice versa. The more stiff a medium is going to be, the faster is it that the sound will travel through that medium. Did that make sense? Now, for your density, that relationship, girls, is going to be as okay inversely related. Which mainly will mean that, okay, yes, your greater density will be at okay a lower speed. And lower speed, as okay, lower density of a medium where that's okay cause a greater speed of sound in the medium. Okay. So if they ask you as okay, what would be as okay a factor, a characteristic of a medium that will cause the sound to travel at the fastest speed. That's going to be okay, a medium with greatest density, greatest stiffness and lowest density. And vice versa. Clear? Okay. So speed of sound is directly proportional to stiffness, and speed of sound in the medium is going to be inversely proportional to the density. Please keep in mind here, okay, when we say stiffness and density, it's okay, we are talking of the stiffness of the medium. We are talking about, it's okay, the density of the medium. But in our case here is okay, what we mean by medium, 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 medium is the tissues. Okay. Now you may also say that, okay, yes. Now the stiffness, yes, okay, is directly proportional. And density of a medium is inversely proportional to the propagation speed. So we can mainly say, okay, what is the actually, that's okay, what is the main determining factor of a medium that has the greatest biggest influence on the propagation speed? And that is still going to be associated stiffness. So R of these two factors here, where one is directly proportional and the other one is inversely proportional, it is still, yes, okay, the stiffness of the medium that has, okay, the greatest influence upon the propagation speed of sound. So you may say, well, okay, I have a tissue which is dense, which is stiff, and it is also dense. You still going to have, okay, yes, a great propagation speed. Although, yes, okay, the density actually is okay. You can say the greater the density is okay, would affect, or yes, okay, would decrease the speed. But it's still, yes, okay, yes, okay, the stiffness of the tissue, which is, okay, yes, the measure of these two characteristics, yes, okay, determine the propagation speed. Did you girls get that? Yes, girls. Any questions? Now, dear ladies or dear girls, at this moment, that was all that I could offer for chapter number 3. Or at least as far as, okay, even as says, okay, the material in the chapter is concerned. Now, what you may find then on page number 40 in your book is, okay, as a summary for the chapter. It's not going to be every chapter that's going to have, okay, something like this. But what can you use the summary for? What can you use the summary for? As a tool of revision. Did that make sense? So girls, let us just have, okay, a little brainstorm before I send you girls on a coffee, tea, refill break. What's the relationship? Okay, now close your books, close everything. Pick up your eyes and look at me. I would need to see more than, okay, as the back wall and your roof, fans and shelves. Good. Good girls. That's better. So what's the relationship between amplitude and frequency?
Directly.
Wrong.
Oh, you said frequency.
And amplitude, they are not related.
No, yeah, they're not related. I don't know why I thought you said
Oh,
intensity.
what the hell are you
Sorry.
thinking about? Okay, that's fine. That's fine. Okay, what's the relationship between frequency and wavelength? Frequency and wavelength. They are inversely related. Because please make sure that you know this one. Okay? This is going to just, okay, become very handy. And when I say handy, I mean it. Clear? Okay. You can even look at the equation of wavelength. You calculate the wavelength by dividing a fixed number, which was 1.54, by the frequency. So if the frequency increases, you actually just, okay, divide that 1.54 with a bigger number, which gives you as, okay, a lower wavelength. Or you can also do as we did, say, yes, okay, period and wavelength were our period and wavelength related. Because you are required to give them some sort of answer. How are period and wavelength related?
Directly.
Directly related. Okay. So period and frequency are, how are they related?
Reciprocal.
Inversely. Let's just go over inversely first. Okay, dear? Okay. Bias, okay, then they become as, okay, reciprocal. Okay. So since both period and wavelength are directly proportional, they are both inversely proportional to frequency. So you can look at it in that way as well. Clear? Okay. Where, okay, that reciprocal relationship is only going to be for period and frequency. That will not apply to period and wavelength. Oh, sorry, wavelength and frequency. Clear? Okay. Why is it only period and frequency that's going to be as okay reciprocal? Because one is going to be as okay the time that it takes a cycle to repeat. Whereas frequency is going to be as okay how many cycles are completed in this time span here. Clear? And the other reason that we say that they are reciprocal, because the times that the frequency increases, the period reduces equally. Which we mainly said, okay, as 1,000 cycles per second, that was a frequency, which could be as, okay, 1 kilohertz, which mainly that would mean that, okay, as the period for each cycle is going to be 1,000th of a second, which make it a millisecond. So kilo and milli, yes, okay, they were reciprocal units. Mega and micro were reciprocal units. Clear? So your frequency is in megahertz. Your period will be as okay in the reciprocal value of seconds, which will be microseconds. Did that make sense? And what makes a number reciprocal? When you multiply the two numbers and the product is 1. So yes, okay, 1,000 seconds or 1,000 cycles per second, which is 1 kilo, multiply by 1/1000. So you divide 1,000 by 1,000, what do you get? 1. You have 1,000 people, you have $1,000. Each person will only get $1. Yeah. Okay. What is the relationship between period? Power and frequency? How are power and frequency related? Dr. Thomas and Dr. Ferretti, look up here. Yes. Okay, don't just look at me. That's not going to give you the answer. The answer is not written on my forehead. Use the mass that is behind your forehead. What is the relationship between power and period?
Unrelated?
Huh?
Unrelated?
Unrelated, exactly. Clear? Okay. Good. What is the relation between density and mass?
Directly related.
Directly related, right? Okay. Okay. So that's okay. Get hit by a 10-ball tennis ball. You may say, oh, what? Okay, that was nothing. But that's okay. Get hit by a golf ball. Okay. You may need to just, okay, go to the emergency room then. Because, okay, that's more density. Because that is packed with, I don't know what the hell they fill in that thing. Cement or concrete or whatever. But anyways, so that's a greater density. Okay, girls? Okay. What's the unit for volume?
Meters cubed.
Or any unit of distance cubed. Or you may not get a distance of a unit of distance being cubed. So what will be as, okay, the traditional unit of volume? that volume or distance cubed is an unconventional unit of volume. What is a more traditional or conventional unit of volume?
Liter.
Huh?
Liter.
Liter, exactly, right, okay, okay. Good. Okay. Okay. Now, if your power increases 10 times, what is going to be the change in your intensity?
Increases
10.
10 times. Increased by 3
Increase
times.
10 times, exactly right, okay. If your amplitude is reduced to 1/3, okay. If your amplitude is reduced to 1/3, what is going to be as okay the change in power?
1/9.
1/9. Okay, good. That's good. You girls got that straight. Good. Okay. What will determine your final power? What will determine your final power?
Would it be your amplitude? How much it decreases or increase?
When the power is
Surely it's going to be the initial power and the degree of decrease in the power. Okay. Is your initial intensity adjustable? Is your initial intensity adjustable?
no.
Oh, yes, it is, my dear.
Yes.
All your three biggest parameters are adjustable, right? As a matter of fact, well, okay, mainly because they were all directly proportional, you can say increasing one is going to decrease the other, is going to increase the other. Clear? And it's mainly as okay, just one knob on your system that mainly as okay can be used to either as okay increase or decrease the bigness parameters of the sound wave that you transmit into the patient's body. That's going to be as okay your power output. Clear? So that's okay. When you look at the console, or that's okay, of your ultrasound system, that knob is most likely going to be in the upper right, upper left side of your keyboard. That there is a knob that you can twist and turn to increase or decrease your power output. And by doing so, that's okay. When you increase the power, you increase the intensity of the sound wave that you transmit. And those will be as okay, greater amplitude waves. So they were all SOK directly related and all SOK adjustable. So that's how you made SOK can kill a lot of birds with one stone. Because okay, these three bigness parameters here, okay, they are all going to undergo the same fate. They will decrease as they travel through the medium. So the power of the sound wave will decrease, which will cause the intensity to decrease, which will cause the amplitude of the sound waves to decrease. So to begin with, that's okay, it may be physically, it's okay, big waves, but as they travel deeper and deeper and deeper and deeper, they become lesser power, which gives them a lesser intensity, which makes them weaker amplitude waves. What is the unit for power?
Watts.
Watts. Okay. Yeah. Hey, ladies. Do you guys recall the audible range of frequency?
Is it 20 hertz to 20,000 hertz?
Exactly right. Okay. 20 hertz to 20,000 hertz or 20 hertz to 20 kilohertz. Right? Okay. Whichever way. Right? Okay. So, now, when we say that a frequency is of 20 hertz, then what will be the period? A sound wave has a frequency of 20 hertz. Then what's going to be its period?
Twenty sound waves a second?
Okay, that's what you mean by, okay, 20 hertz. But my question is, what is going to be the period? You said 20 hertz means 20 cycles per second. So what is going to be the period then?
1/20?
1 or 20 what?
Microseconds.
No. Why would it be microseconds? Dr. Thomas, why would it be microseconds?
1/20 seconds?
1 or 20 seconds. Clear? Okay. It is not going to be microseconds, my dear. That would have been microseconds if we are talking about is okay. A 1 or 20 microseconds had we talking about is okay, a frequency of 20 megahertz. Okay. Where 20 is, or we can say, okay, 1 or 20 would have been as okay, reciprocal to 20. And when you mean it says, okay, microseconds would have been the reciprocal of a megahertz. So those of you who still are confused on that need to just, okay, look at their frequencies versus period. We can take calls, listen, we can take any number. Let's do it this way. Because what we mainly say is, okay, that they are reciprocal is that whatever number we have is going to be reciprocal. Now, if you find this, okay, here said hertz, and that's okay, it is going to be second. If you said 20, and 1/20. But here we said, now these two numbers here, 20 and 1/20, they are reciprocal, right? But if yes, okay, here go from hertz to then, okay, yes, kilohertz. Then yes, okay, the reciprocal of kilo is milli. So the period become 1/20 of a millisecond. Clear? Whereas we now then say as okay, 20. We say as okay, go hertz. Or we go and say as okay. And okay, now the reciprocal of 1/20 is still 1/20. But then we go and say, and the reciprocal for the hertz was going to be like this. Or unit. Well, then we can say, okay, since now we go mega, then this now here is going to be as okay, micro. Which mainly means that, okay, if we had a frequency of 20 megahertz, then the period is going to be 1/20 millionth of a second. Because mega and micro are reciprocal units. Clear? And that's mainly because, okay, these two factors here that we compare, which was respectively frequency and period, were reciprocal. But you can say, okay, 20 multiplied by 1/20. What does that give you? That's 1. You can say, okay, 20,000, because that's what 2K would mean, 20K would mean. Divided by, as okay, 1/20,000. It's going to be as okay, 20,000 multiplied by 1/20,000. These will still cut out one another as okay, yes, this. And so here is okay, 20 million divided by as okay, 1/20 million. Or multiplied by 1/20 million. Still comes out to the same. Did you girls get that?
Yeah.
Okay. Now, let me just ask one last question. These were our two transducers. And we were scanning. Skeletal muscle. So this was one transducer. Producing is okay, this sound wave here. With this frequency. This was our other transducer producing this sound wave here. Now, as these sound waves from these two transducers here travel through the skeletal muscle, which sound wave will have the greatest wavelength? A or B? Which producer will produce the greatest wavelength in the skeletal muscle?
Would it be B?
Okay,
Couldn't they both be the same?
Yeah, I thought because they're
they'll
Going
both be the
to-
same, exactly.
they're
Why?
Because
going
it,
to, go
It's
ahead,
the
Mary.
same tissue.
Mhm.
So same tissue, that's going to be as okay, will be the same speed. So neither of them, they will both as okay, be same wavelength because of same speed. That's okay, go. Now, what do you have at the end of this chapter here? A bunch of questions, right? Right? What would I recommend you girls do? Try to do them. And that's not enough. Let me give you some other bones to chew on as well. Because, okay, what do we have at the end of the book? What do we have at the end of the book? An exam review, right? And let me just see, it's okay, where those questions start from. Good. So here's what you will be spending your next hour doing. Yes, okay. Questions 1 to 33 from page 41 to 46. Then question 50. OMG. That may be a weekend project. Let's see. 138, which goes from page 432 all the way to page 451. So should we say that I see you girls? At 12:30. And by that time, yes, okay, you should have done this. Or as much as you can. Okay. And have had your lunch.
So what time are we coming back?
12:30.
Okay.
But yes, okay. It's a lot. Okay, girls, just look here. It was the 32 questions at the end of the chapter, but I was okay also from question 50 to 138. From page 432 to page 451. That's okay. These are made as okay in the exam review. Those are chapters, or those are questions for chapter number 3. See you ladies then, and then we'll right cover up the answers. Don't look at them. Okay. Any question that you have a hard time, it's okay. Just skip and okay, let's proceed on to the next one. That's fine. Okay, girls, welcome back. Okay. So what are the questions? Okay, girls, let's see what we can do, okay? So let's go on to yes, okay. Oh, okay, yes, it's okay. Page 41. Question number 1. Right. Now, what are the units of? Wavelength, that's going to be yes, okay. Mainly yes, okay, just any unit of length. Or distance. Only, not squared, not cube, not whatsoever. Clear? And the unit that we have for wavelength or distance is millimeters. Clear? Okay. Next is frequency. Okay. And the unit for that could be as okay. The actual traditional unit is hertz. But here we can mean it as okay, a hertz that is mean it's okay, going to mean it's okay, cycle per or cycles per second. Intensity. Now it's going to it's okay based on it's okay because a unit power per area, which would be watt per centimeter square. As long as okay as it is a unit of power, a watt, fraction or multiple, and any unit of distance being squared, that should be as okay, making up an area, and okay as power versus area or versus per area is going to be the intensity. Okay. Next is what we say is okay, propagation speed, which is made as okay, that's going to be the same as speed, which is going to be as okay, just be n distance, not squared, not cubed, covered by as okay per time. Okay. So that can be as okay, any unit of distance, meter, kilometer, mile, centimeter, micrometer, whatsoever. Okay, per unit of time. Okay, which could be day, hour, minute, second, millisecond, microsecond, and so on. Now, period. Simply as okay, just unit of time. So that's okay, pretty much okay as any of the units that we have here. Could also as okay be units for period. And power. We already had power earlier, which was this one here. Okay, so we can say it's okay. It could be watt. It can be as okay kilowatt. It can be megawatts. It can be as okay milliwatts. It can be as okay microwatts. Okay. Any questions here?
And that's for period that you just said about.
Period. Any unit of time, and that's why I say any of these units here can be a period. Maybe say time, what else? Okay, I mean, it's okay. Time here, it's okay, that's the same as we had in speed, right? So any of these units of time here can also be as okay expressed as a period. Simply. Did that make sense? Now, question 2. Does the medium or the source determine these parameters? So that means that's okay, that's pretty much okay, as asks what determines as okay our parameters here. Now goes as I say as okay wavelength. That was both source and medium. As a matter of fact, only parameter determined by both source and medium. We said frequency. Now frequency of the sound wave, that is going to just okay be determined by the source only. And what we here mean by the source is going to be as okay the transducer. Okay, I'm just going to skip yes, okay, the intensity for now. And just as okay, go on to propagation speed. And okay, as we have mainly as okay been talking about this the whole morning is that I was going to as okay be the only of the 7 acoustic parameters to be determined by medium only. Every here it's okay mean that that's going to be as okay the tissue. Likewise, period. Just like frequency, source. And by the source, yes, okay, we mean the transducer. Now, guys, if you look here at your 3 bigness parameters, which is okay, yes, they give you power. They gave you, yes, okay, intensity. And they give you, yes, okay, amplitude. But what they wrote here in a bracket for all of them is initial. Now, since it says initial, that is going to just okay make it the source. Where here is okay by the source, that's okay, that actually is okay means that's okay, what would be as okay, the ultrasound system. Is that clear? Whereas ladies had it said final power, final intensity, or final amplitude, then the final of all of these 3 bigness parameters here is going to be as okay, primarily determined by initial power, intensity, or amplitude. And the other factor that will determine your final power, final intensity, and final amplitude is going to be the degree of decrease in the power, intensity, and amplitude as they travel through the tissues. Okay. So that mainly is okay, you can say it's okay, that final power is going to yes, okay, be determined by the initial power, which is determined by the source, and the degree of decrease in these 3 bigness parameters. Where the degree of the increase in the bigness parameters is going to yes, okay, be determined by the tissues. Okay, so a factor that's going to just okay determine how much as sound waves power decreases as it interacts with the tissue is going to be as okay the nature of the tissue itself. Clear? Okay, girls. So here's okay. The answer is system or source mainly because okay, they ask of the final initial intensity or power or amplitude. Whereas had it been final, then it would have been the initial power, initial intensity, and initial amplitude. And then also, yes, okay, the tissue. Are you girls clear upon that? Any questions about that? Or how that makes sense? No? Okay. My job was to ask. Now, using a particular ultrasound system and transducer, which of the following cannot be changed by the operator? Now, just keep in mind here that, okay, it says, okay, we can say, okay, particular system. And then we see as, okay, transducer. Okay. So which of these following parameters here can be changed, which cannot be changed? Or it's made as, okay, just indirectly asking, are these parameters here adjustable? Or are they not adjustable? Now, goals, we already said, again, as okay, and since we are using as okay, particular system and transducer, the wavelength that's not adjustable because it's a particular transducer. Okay. Next is frequency. And again, that's okay. Mainly because that's particular transducer that makes it not adjustable. Although it's okay, there are common transducers that we have nowadays, or what you can call as okay, broadband frequency transducers. Where okay, yes, in that case, that's okay. That would not be as okay saying okay, a particular transducer. Then okay, as the frequency, yes, okay, is adjustable. Then you actually have a range of frequencies that you can work with them. Okay, but for this case, yes, okay, mainly because it says okay, it's a particular transducer and or system that makes yes, okay, not adjustable. Now, ladies, the intensity. That was adjustable. Pretty much okay, yes, by helping us, okay, or we can say by adjusting us, okay, the power. Which made us okay, just what we had later further down is going to be as okay, the power. It's also as okay, going to be adjustable. And so is okay as the amplitude. So they are all just okay, increased or decreased by increasing or decreasing Or we can say, okay, adjusting the power. Okay. Last but not the least is going to be okay, the wavelength. No, sorry, propagation speed. Now that is not something that we can adjust. We don't have a knob where we can increase the speed or decrease the speed for the sound wave. That is going to just okay, pretty much okay, as change as it travels through the tissues. And that irrespective of the wavelength of the transducer, that is irrespective of the frequency of the transducer, it is irrespective of all of our three bigness parameters of the transducer or system to which we have adjusted it. Whether we increase the intensity or decrease the intensity, when that sound wave is okay, travels through a specific tissue, it's going to just okay, has its own speed.
Has its own what? What did you just say? It has its own what?
It's going to just okay, be traveling at its own speed. Idea whether that is a 200 watts sound wave. Or whether that is a 2-watt sound wave. And both of these just okay, travel through the same tissue. Let's say that this was bone. It's going to be traveling at the same speed. So just because you increase the power of the sound wave, that's not going to make it travel faster through the bone. Or just because, okay, reduce the power of the sound wave, it's not going to make it travel slower through the bone, or vice versa. Likewise, as okay, whether you is okay, have a higher frequency or lower frequency transducer, it's not going to, as okay, determine or change the speed at which sound is going to be traveling through the bone. That speed is determined by the tissue itself because, as okay, here it's a bone. So you can't adjust it, right? Propagation speed had been adjusted, but that you say, well, okay, I'll increase the voltage. Or sorry, the power of yes, okay, the sound wave. And that's going to make it yes, okay, travel either faster or slower through the bone. That's not how it works. So yes, okay, propagation speed is not adjustable. Did that make sense? Question number 4. Now, true or false? Now, be watchful, girls, because yes, okay, whenever you have a statement, some part of it may be true, but it's okay if it other part and it's okay, maybe false. It becomes false. For a statement to be just give me a second. Okay, so for a statement to be true, it has to be true from the beginning to the end. Okay, That's how true and false questions will work. Now, what it mainly just says here is it true to say that a frequency or a wave with a frequency of 15,000 megahertz is that going to be as okay ultrasonic? Yes, it is ultrasonic. Why? Because it's okay, this number here is greater than 20 kilohertz. And they said, is it true that a frequency of 15,000 megahertz is ultrasonic and can be used for diagnostic imaging? It has said, okay, yes, and can be used for diagnostic imaging, then that would have been false. Because 15,000 megahertz is far, 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 far beyond the normal range of your ultrasound frequency. Okay, we said that, okay, the upper range was 15 megahertz. That was okay as the max normal frequency of, okay, yes, an ultrasound wave. As a matter of fact, yes, okay, these 15,000 megahertz here, that's actually going to be equal to 15 gigahertz. Okay, so 15,000 megahertz is 15 gigahertz. Is that clear? Okay, but we can maybe say, okay, any frequency greater than 20,000 kilohertz is going to be as okay ultrasonic, because what we call ultrasonic means is okay something which is above the human ear's ability to hear. Did that make sense?
Yes.
Good. Question number 5. Again, yes, okay, asking true or false. Now here it says, is it true to say that, okay, yes, if the amplitude increases 3 times, that the power, well, they're talking about the intensity, increases 6 times. And that is false. Okay. Now, you may say that it's true because you didn't know, yes, okay, that amplitude square would mean that, okay, as if it increases 3 times, that 3 needs to be squared, which means, yes, okay, it doesn't mean 3 multiplied by 2, but actually mean 3 multiplied by 10, 3 multiplied by 3, which means it will come 9 times, which is going to, yes, okay, that 9 times is going to be, yes, okay, the actual change in intensity. Yeah. So for this statement here to have become true, yes, okay, it should have said 9 times, then it will be true. But since it says 6 times, then it's going to be false. And just also watch out for the increase and decrease. Because, okay, if it said that, okay, as the amplitude increases, let's say it's okay 3 times. And the number here is 9 times, not 6, but goes decrease, then it's still wrong. Okay? So and that may as okay mainly be because you say, well, okay, yes, you didn't realize that okay, yes, amplitude was directly proportional to intensity, which mainly mean that okay, yes, if one increases, then the other also has to increase. Did you ladies get that? Any questions? Okay. Now we have a figure. Let me just see if I'm able to just okay somehow reproduce it. So we can say this. And okay, there are different things that they have marked. So we go, yes, okay. E. There's something here is okay, which is B. There's okay, that's where we go. You can say D. And okay, there's something here is okay, which is C. Now, question number 6 may is okay, just ask us, okay, as which of the following best describes the line identified by the letter E? And what we have is okay, as amplitude, period, frequency, wavelength, and peak to peak amplitude. Clear? Now that peak to peak amplitude goes. Now some may think, okay, yes, will it be this? Should this? No. We can make it okay from the peak, or you can say okay from the positive peak to yes, okay to the negative peak. This whole range is okay. That's going to be it's okay what we call a peak to peak amplitude. Clear? Okay. We can make it as okay from here to here. Yes, okay. That will be period if we measure it in time. From here to here in distance, that will be the wavelength. Clear? Okay. And because I said from here to here, this, or on the other hand, this to this, either of these was going to be its okay plane amplitude. Okay. But when we go from the very top of a wave to the very, very bottom of the wave, that range is going to be referred to as the peak to peak amplitude. Did you girls get that? Okay. Now question number 7 is okay, which of the following is okay best describes the line identified by B? B as in boy. Which is this fellow here? And we say it's okay, amplitude. Well, okay, that cannot be called as okay, the amplitude is going to be as okay, you can say vertically represented. Peak to peak amplitude, no. Frequency, no. Wavelength, no. None of the above. Yes. Because this here is okay, does not represent wavelength. I said this here will be wavelength. Right, okay. Frequency will mean is okay, means okay, if we went all this and say, okay, how many cycles do we have in this period of time? And that okay, what's the frequency? That's not what we can say here. Okay. So that's okay here. None of these options, that's okay, actually, that's okay, represent B. Or we can actually say here, B actually is okay, is equal to nothing. It may as okay, cause up okay as we can say okay, 2 cycles or 3 cycles. Is that clear? Question number 8. Which of the following is okay best describes what is identified by the letter C? And that's why I just said earlier. This here. That says okay, that's the amplitude. Because what did we say that we describe amplitude? Here I made is okay from the average line, which is this fellow here, to the peak, or from the average line to the trough. Right? So this would be as okay, either this, since that is okay, represented by C, would be the amplitude. Had C been up here, just like this, then that would also have been as okay, because as okay, the amplitude of either this wave, or this wave, whichever. Did that make sense? Now question number 9. Which of the following lines above A, B, C, D is most likely could be as okay, reciprocal to frequency? Just keep in mind, guys, they are not asking inversely proportional. Okay, they are not asking reciprocal, yes, okay, inversely proportional. They are asking reciprocal. Okay, and the only thing that is going to be as okay, reciprocal to the frequency is period. And when we look at okay as at D, it means okay from as okay the same point on one wave to the same point on a following wave. Will be the period. Or we could have said, well, okay, if we start here, it goes here. This here is okay, measured in terms of time. That will become the period, or one cycle to complete. Or we could say it's okay from here to here. That's still is okay the time that it takes one cycle to complete. Because okay, the last of this cycle is here, then okay as this, and then okay as here. So that will be the period. And that is going to, okay, that's going to be the only one that is reciprocal to frequency. Or we can say, it's okay, line D is okay. If we measure it in time, it's going to be the period. If we measure it in length, then it becomes the wavelength. But it was only going to be, okay, the period that will be reciprocal to frequency. So question 10 is okay, I mean, yes, okay, already said that. Since this from here to here, or it's okay, from here to here, represents the period, but that only measured in terms of time. It's also as okay, going to as okay, represent the wavelength if we just okay, for instance, okay, measured in terms of distance. So what it means that okay, which of the following lines is identified by the letter D? Clear. Now it can't be amplitude and frequency and peak-to-peak amplitude, but it is wavelength. Because the same that we just said was identified by identifying or marking the period. But when we measure it in the length, it becomes the wavelength. Is that clear? Question number 12. Which of the following is okay is best describes what is identified by letter D? The same. Same question, just asked in a different way. Because okay, what the hell here is okay, amplitude, peak-to-peak amplification, or amplitude, sorry, frequency, period, and none of the above. So D is okay, it's still going to be period. In question 9, they may ask, okay, just which of the following are about is okay, reciprocal to frequency, which was D. Question number 12. Which of the following lines or which of the lines above is okay, A, B, C, D, or A, B, C? Okay, sorry. It's most likely to be determined by the source and the medium. Which of the following lines above is going to be determined? It's more likely going to be determined by source and the medium. And that will be B. Okay, all I says again, nothing else. Okay, it's okay, it could be, it's okay though. So we can say, okay, may represent just okay the propagation speed. Clear? Okay. A and C. What does A represent? Peak, amplitude, and C is okay, represents simple amplitude.
So D can be period and wavelength?
B as in boy.
B
No, D as in dog, sorry.
Yeah.
Can be
so
period and wavelength.
But how would you know? Because I think that's why I got confused, because I associated with one.
You just have to look out for the options.
Okay,
In question 10, what are your options for D? Or what options do you have to choose from? You
That
have
would be-
amplitude. Okay. Do you see a period in question 10 as an option?
no,
Okay, good. In question 11, do you see wavelength as an option?
no.
No. And what I said the other day when we talked wavelength, and period. I say, well, okay. This is your wave, or this is one cycle. When we measure the time from A to B, or we can say, okay, from beginning of wave to end of wave. When we measure this in time, that is going to be called the period of this wave. Did that make sense?
Yes,
Good. And when we talked wavelength, I say it's okay if you still measure it's okay from A to B, but you measure this in terms of length or distance, then that's going to be it's okay the wavelength of the wave. Because it's okay, the second or third word in the definition of period is the time. Likewise, the second or third word in the definition of a wavelength is going to be as okay, it is the length or distance. And then just comes as okay, what that time for period or what that length and distance for wavelength is okay accounts from. From beginning of cycle to end of cycle. Or we can say okay, from beginning of cycle or one cycle to beginning of next cycle. Because most likely as okay, after this cycle here is okay, there may be as okay, you may have another cycle. So that's okay. The point is okay, the first cycle finishes, that's going to be as okay where the second cycle will start. So from the start of this cycle to the start of the next cycle, or from the start of this cycle to the end of the cycle, when we measure that in terms of time, that will become period. When we measure that in terms of length or distance, that becomes wavelength. Did that make sense? And that's why we mainly said that, okay, as the greater the length or the greater the time, the greater the wavelength. So we can say, okay, here we may have, okay, as this pink wave here is okay, is going to be as okay, a wave with a great period and a great wavelength compared to, let's say, as okay, let's take this wave here. Or let's say it's okay, let's take, okay, yes, these two waves here. Where you may say, okay, this will be the period if we measure it in time. And likewise, that's okay, it will also is okay be the wavelength of this yellow wave here. Is okay if you measure it from year to year in terms of length. So for this one here, this will be as okay the period of this second orange or yellow wave here, which is going to be as okay it's wavelength if you measure it in time, measure it in terms of length and distance. So pretty much okay, as based on this, we can say as okay that period and wavelength are directly proportional. Because the bigger the time it takes the wave to complete, the greater is going to be the wavelength. The lesser time it takes as a wave to complete, the less shorter is going to be its wavelength. Did you get that? And that's what makes them directly proportional. Any questions? Fish? True or false? And again, I love true and false questions. So is it true or is it false to say that, as if the power of a wave is halved? That the intensity is going to be reduced to 1/4. Now, as far as we can say, it's this part here and this part here is concerned, that's true, right? Because it says, when we reduce the power, the intensity will reduce. But then this relationship here is wrong. Because, if the power is reduced to 1/2, then your intensity is also going to be reduced to 1/2. Okay. This would have been true had they said amplitude here. The amplitude that's is reduced to its 1/2. Then yes, your intensity was reduced to 1/4. That would have been true. Or even if I said power here and it's amplitude here, it would still be true. Did that make sense? So that's all of a sudden, just just flipping around with things, that's makes a question's answer just different. Okay, girls? Any questions? Anybody in doubt? Question 15. Oh, that's this is a kind of question that is you may come across. So we can say, we have as a medium 1. And we can say, we have a medium 2. No, that's what the medium is I'm going to talk about here is going to be we can the stiffness and density. If that's true, right? Okay. So medium one, what does that have? Well, okay, so we can say, okay, it has a stiffness of, or it has a density of 9 and a stiffness 6. Whereas medium 2 has a density of 8 and stiffness 6. And then they may just, okay, just ask us, okay, which of these medium here has, okay, has the lowest speed. Now that comes as, okay, now you have to just, okay, know your relationships. Now we already know that, okay, a relationship is directly proportional to speed. Oh, sorry. Speed is directly proportional to relationship. Sorry, what the hell am I saying? Sorry. Your speed is directly proportional to the stiffness. But what we see here is that it's okay, both media has the same stiffness. So as far as, okay, as we can say, it's okay, the stiffness affecting is, okay, the propagation speed, that's going to be the same for both the medias. Clear? Okay, so we say as, okay, the stiffness here is, okay, it's the same. But, okay, now we go on to just, okay, the other factor here, and say density. Well, okay, one has density of 9, one has a density of 8. That is, okay, back in gram per centimeter cube or something like that. Gram per centimeter cube. Clear? Okay. But now they say, well, okay, lowest speed. And we know that, okay, as speed is inversely proportional to density. So the main thing that you just need to have, okay, if we are looking for the lowest speed, we will need to look for the greatest density. So it's going to be medium, one of these two here, which will have the lowest speed. Did that make sense? That, okay, had they asked you for, yes, okay, let's say it's okay, the greatest speed, and these were the characteristics, then you may say, okay, greater speed, that may mean that we will look for something with the lower density because the stiffness was the same. So that would have been medium 2. Did you girls get that? Question 16. Now, pretty much, okay, same kind of thing as, okay, asked in a different way. Okay, so which of the following characteristics will create the fastest speed of sound? So the may as, okay, just ask about as, okay, greatest speed. And we know that speed was directly proportional to stiffness and inversely proportional to density. Clear? Okay. Which means, okay, now when we are looking for the highest speed, that will mainly need that, okay, that we need to choose the one with the lowest density, which is B and D. And then you just go on with the next one and say, okay, yes, highest speed is going to just, okay, be greatest stiffness because they were directly proportional. So the one with the lowest density and the highest stiffness is going to have the highest speed. Had to ask the other way around. and says, okay, lowest speed, then that would be the ones with the greatest density and the lowest stiffness. Did you ladies get that? Ah, okay. That's probably okay. What they is okay. So the blue one here, that's me is okay. What you just get from question 17. Okay, girls. Question number 18. 1-8. Who have tried to answer that? Okay. Who had issues with this question? Okay. Then Lord help you. So what do we have? We can say as okay, the power in a beam is 1 watt. Right? And okay, yes, the area is 5 centimeters square. And they simply as okay, just ask yes, okay, what is the intensity? So Gauss' intensity was nothing but just your power by area, where you know, so okay, just put in the values. 1 by 5. And yes, okay, then or yes, okay, would know that okay, as the unit was going to yes, okay, be watts per centimeter square. So goes 1 by 5. That is mean it's okay, just a fraction, which in terms of decimal can be written as 0.2. Just look at it in this way. You have a cake. And you have 5 people. Clear? Now that cake might have been sliced into 10 slices. So how many slices each person going to get? 2 slices. But since you cut the kite into 10 slices, that's okay. Each slice is going to be 1/10 of the cake. So 2 slices, that is going to be as okay, 2/10. Or you can even go the other way around and say, that's okay. Oh shit, sorry. Is my math correct? That I choose as okay 1/2 because it's going to be as okay or 1/5. Well, okay, you can say it's okay. If I multiply this that's okay. It's okay, go like this way. All right. Why did we do that? So it goes. There is a V 1/5. Sorry. As you made it, okay, multiply that. It becomes 5. It becomes 1. Which would have been this. Or maybe you can say it's okay, you multiplied by the reciprocal of this number here. And the reciprocal of this number here is 5. But you multiply as okay the value here. So does that become 1? Yes. Because this multiplied by its reciprocal, yes, okay, still becomes 1. Clear? So whether it says, okay, 1 or 5, or whether it says 2 or 10, or 3 or 15, it comes out to the same. 1/5 and 1/5 is 0.2. Or you can go into currency mode and say 20 cents times 5 is $1. So 1/5 of $1 is equal to 20 cents. Which is going to say, okay, 0.2 of $1. Clear? Question 19. Now, if the intensity remains the same. Now, who had issues with this one? Who had issues with this one? Yeah, because this one here is a little tricky. Not just a little tricky, it is tricky. So let's see what the hell happens. So it mainly says, okay, if the intensity remains the same. Is same. But what I mean, we can make is okay, say that okay, we can check okay as 2 units, 2 yes, okay, intensities. And say, well, okay, it's still going to be it's like a 10 watts per centimeter square and 10 watts per centimeter square. Right, okay. While the power is doubled. Clear? What happened to the beam's area? Now, we can make this okay, our final intensity is okay, still remains the same. Although it's okay, in one case, the power might have doubled because it's okay, it's 20 watts. But the intensity still remains the same, and that's mainly it's okay because the area also doubled. Clear? So what it actually is okay will become as okay because we say here 10 watts per centimeter square. That's how it's become. But okay, we double the power to 20 watts. Okay, now had it been 20 watts by as okay, 1 centimeter is okay, then we could say as okay, then the intensity is okay, would have doubled. And then would not have remained the same. So it says, okay, keep the intensity the same as 10 watts per centimeter square. That's why we says, okay, we have to double the area too, from 1 centimeter to 2 centimeters. And that's when it goes on, okay, as when we calculate it like this. And so it's like a 2 or 20 divided by 2 still becomes 10. The unit is still going to say, it's okay, this. So the power still, okay, the intensity still remains the same, although it's okay, the power was increased or doubled. Clear? But here they ask us, okay, to keep the intensity the same, although it's okay, the power is doubled, what else needs to be done? The area also needs to be doubled. Here it's okay, the power increased, mainly because, okay, so that's going to cause, alone it was going to cause an increase in the intensity. But that possibility is made as, okay, what they excluded in the beginning is, say, okay, keeping, or if the intensity remains the same. Clear? Okay, so to keep the intensity the same as okay, by doubling the power, we also need to double the area. That doubling the power is okay, will cause a doubling of the intensity. Doubling the area is going to just okay, reduce the intensity because intensity and area are directly or inversely proportional. So actually, as okay, here is okay. Doubling the area is going to just okay. Half the intensity. But which is not going to just okay affect the overall intensity because okay, we also did the opposite to the power. Maybe actually it's okay. Double the power. So you can actually say, okay, doubling the power and doubling the area is going to just okay, cancel out each one another. And here's okay, the power and the intensity at the same. Did you girls get that? Any questions? Question 20. Now sound being traveled is okay at total distance of 10 centimeters. Clear? In 2 seconds. Now what they mean is, okay, just ask us is, what is the speed of the sound here? And that's pretty much okay as just doing as okay your math. 10 centimeters or 2 seconds. So that means it's okay, just makes it 10 divided by 2 becomes 5 centimeters per second. Are you guys clear about that? Now just be aware, girls, it's not going to be as okay necessary that you'll be given 5 centimeters. You may be given something like, okay, as zero point 0.05 meters per second. Okay, that could be the case.
So in that case, sir, you convert it over to centimeter before you can find the answer, right?
No, you don't. You convert 5 centimeters into meters. Because, okay, what we got here was the speed in just, okay, centimeters per second. But you may not necessarily be giving us, okay, the answer in centimeters per second. It can be meters per second, it can be micrometers per second, it can be millimeters per second. So in that case, that's okay, you may have just okay convert from centimeters, which is okay, you did from your original math from the equations, or it's okay from the values given, to it's okay to see if it matches out any of the answers. So if you don't know how many centimeters there are in a meter, then you will be LOST. Question 21. And again, it's okay, true or false. So is it true to say that, okay, as your propagation speed will increase if we increase the frequency? No, that's not true. Why? Because these two fellows here, yes, okay, are not related. So it really doesn't matter whether you increase or decrease the frequency. It's not going to just, okay, cause an increase or decrease in the propagation speed. Yeah. They just ask the same thing, yes, okay. In another way, yes, okay, in the next question, and say, yes, okay, is it true to say that, okay, yes, the propagation speed increases if the frequency decreases? That's again, yes, okay, going to be false because propagation speed was not related to frequency. So when two things are not related, you can change one in whatever crazy way you want to. It is not going to have any effect on the other. Question 23. Again, it's okay, true or false. And okay, as it is true or is it false to say that the propagation speed does not change as frequency changes. That's true. Which means, okay, what I just said. Because what does it mean? Yes, okay, change frequency, for instance. You can either increase it or decrease it. But that change in the frequency does not cause a change in the propagation speed. So since it's okay, they put that makes it true. Has it only said this, then it would have been false, just like question 21 and 22 were false. Right, okay. So goes when I said that, okay, a second paragraph of propagation speed determined by thing was important. You can see, it's okay, how you may be asked. Did that make sense? Question number 24. Now they made us, okay, just asking us, okay, what is the wavelength? And the only factor that you have been given is a 3 megahertz frequency sound. And they were not a-holes. They made us, okay, so, well, okay, we are still talking of, okay, as soft tissue. So yes, okay, what are the factors that we need to know? Yes, okay, or we can use, because, okay, from soft tissue, the thing that we got from that was, okay, that 1.54. And then yes, okay, the only other thing that we needed was, okay, as the frequency of the transducer, which was 3. And it has to be as, okay, in megahertz. Right, okay. Where you mean is to say 1.54 divided by 3 is roughly speaking 0.5. And we already know that, okay, as here as well as, okay, the unit here was millimeters. So your unit of the wavelength was going to be millimeters. So that's going to be as, okay, the wavelength. So here's, okay, you see it's, okay, the same number, but with different units. Okay, it says 5 meter, or okay, 0.51 meter. This is half a meter. 0.51 kilometer, which is half a kilometer. 0.51 millimeter, yes, okay. Which is okay, that's what we have here. Okay. 0.5 nanometer, and nanometer is okay as the billionth of a meter. And okay, then the micrometer is in a millionth. So it's okay, the unit that we use here is going to be micrometers. No, it's not micrometers, sorry, millimeters, sorry. Clear? Any questions? Any questions, girls?
No.
Good. Question number 25. Now here's okay, what this says, okay, what is the wavelength of a wave with an unknown frequency traveling through soft tissue? Okay. Now practically, yes, okay, that should have been unknown because we really don't know the frequency of the true transducer. But it's okay, then you have to work out from the options that you have been given here. Here's option 1, 0.51 microseconds, that's time. You says, okay, 0.5 meters per second, or option B, that is speed. 0.41 pascals, that's pressure. 0.4 watts, that's watts, that is power. 0.51 millimeters, that's the only one that represents wavelength. Clear. So mainly that's okay because it is okay as a unit of wavelength or unit of length. That's why it's okay, that can be as okay the correct answer. Now, I mean, it's okay based on the values here, we can say it's okay. It's okay, if that's the case, it's okay, that would actually mean it's okay, the same, it's okay, 3 megahertz frequency transducer, but that's not what they're asking us here. Great, so that says, okay, do you know what is the unit of wavelength? Just okay, as a tricky way to just okay, I'll ask you about that. Did that make sense? And question 24 is, not 24, sorry. Question 26 is pretty much okay as the very same here, but just the wavelength. And again, it's okay in soft tissue where, okay, so our frequency is 2 megahertz. And that equation or that was already okay solved in your book, in the text. And when I say it's okay, just memorize, okay, as what 15 or 1.54 divided by 2 is going to be. Clear? That's okay here. Is okay. The unit is millimeters because of our wavelength. Now, ladies, what you girls will have for homework is just okay. Read chapter 3 again, because now we have chalked off all the 7 parameters. Okay, so now you have okay, some more concise. That's okay. Or look at it, and what I recommend is that you do. It's not available to go to the beach anyway, so you have some nice questions in the exam review at the end of the book that needs to be answered and practiced.
So, sir, basically what I'm saying, we're not gonna have any summer. Our summer is gonna be physics.
You will bye-bye for summer for life.
Okay.
Nah, probably not. So, okay. And okay, yes, then we can look at those. That's okay. We can look at the questions tomorrow as well. Right. But there's not much of a point of me as okay giving you girls all the answers and the explanations. Try to go over them yourself because that's practice. That's practice that you don't pay for. Yeah. When you go for your board, just okay, you pay for that. That's $220 out of your pocket right there. And that'll be as okay an expensive way of practicing answering questions. Clear? So make sure that you have your practice before you okay, you sign up. Okay, girlies. So I will see you ladies tomorrow. With let's say it's okay, the exam review for chapter 3. And let's see if we are going to be able to just okay start off with chapter number 4 as well. Okay.
Sir, so the quiz for next week is chapters 1 through 5, right?
Yep.
Yes, no?
Yeah.
Okay.
So we need to speed up our horses. Have fun.
Okay, good night.
Thank
Good-
you.
Okay,
Thank
good night.
you.
Okay.